Good morning, friends. I warm welcome to all of you in the series of statically determinate beams. Today we are going to discuss about the bending stress in beams. Now let us recall what we have studied up till now in the previous series. In the previous series we have discussed the introduction of the bending stress. We were discussed about the pure bending and the small part of an equation derivation, that is f over y is equal to E over R. We have derived this equation and discussed what is the effect of this equation. So the today's session objectives are: understand the concept of pure bending, understand the concept of moment of resistance and section modulus, describe the behavior of beams under lateral loads, derive the bending equation and discuss the significance of assumptions made in the deriving the equation, and draw the bending stress distribution diagram and to calculate maximum normal stresses in a given beam. Now let us revise that we have discussed in the previous session. If we take any section of a beam and consider the free body diagram on either side, we find that there must be the three internal stress resultants at the section in general to maintain the equilibrium conditions. These three are the bending moment, shear force and axial force. So we are discussing the effect of bending. Refer the figure. This is a given simply supported beam with the external loadings. If we take a section right now over here, so at that section, if we take a free body diagram of the left section, the three component will be developed: horizontal force, vertical force and the moment. This moment creates a couple. You just visualize the compressive force and the tensile force, which creates a couple at a section of a beam. Hence, under the effect of lateral loads, the beam bands and the longitudinal axis takes a curved shape. The beam produces an internal resisting couple to balance the bending moment due to applied loads. This couple is generated by the normal compressive and tensile forces in the section. Now let us discussed the bending stress. Let us revise shortly. The beams bend due to the effect of lateral external loads and take a curved shape. Hence the stresses produced due to bending moment is known as bending stress. Also we have studied the concept of pure bending. Refer a figure which is subjected to the 2-point load of equidistance from the support, and because of that at the central region between 2-point loads the zero shear force is developed, no shear force is developed in this region, and hence you can visualize constant bending moment will be developed in this region. This is known as the pure bending, or the stresses generated in this section between these two loads is known as the bending stress, pure bending stress. We have also derived a part of an bending equations. A beam, its sections has been discussed, AB and CD. The layer under discussion is EF distance Y from the NN, that is the neutral axis or neutral layer. When the external load applied, my beam bends at radius R curvature. Y is the depth of layer from the neutral axis. Then, as we discussed in the previous class, all these things we have discussed in the previous class, and we found out an equation, that is the strain in the layer EF is equal to Y by R. Then we found out the stress variation and we find an equation F by Y is equal to E over R. So since it is to be noted over here that E and R are constant and the stress in any layer is directly proportional to the distance of the layer from the neutral axis. Hence, this equation shows the variation of stress along the depth of beam. So, the variation of stress is linear. Let us discuss the same thing on this table top and then we will proceed with the next work. Let us be understood over here. Now, the equation is this: F over Y is equal to E over R. For a given beam, this term is constant. Therefore, I will say that F is directly proportional to R. Means Y, which is increasing, the value of F goes increasing. If Y goes decreasing, the value of F goes decreasing. Then what is the Y? If we discuss the Y, then this is the cross section of my beam. This is neutral axis. Then this is my layer which is under discussion and this is Y. Then my bending stress on one side increases. As the Y increases, the value of stress is also increases. As such, Y becomes 0, the bending stress becomes 0 and that is at neutral axis. Then once again Y increases, my value of stress going on increases. So this is known as bending stress distribution diagram. This is known as bending stress distribution diagram. Now, it has been observed over here that at the top the value is of compressive stress and at bottom it is tensile stress. So the nature is also different. So one is of compression, another is of tension. This creates couple. Now let us go ahead with the today's session on this PPT. So please refer, in this case all the layers below the neutral layer subjected to the tensile stresses, while the layer above the neutral layer, that is the neutral axis, are subjected to the compressive stresses. Please refer this figure. This is the cross section is there, this is neutral axis or neutral layer is there, this is the total, that is the depth of beam, this is the d by 2 half of that. Then from the neutral layer, the above part subjected to the compressive stress, the bottom part subjected to the tensile stress. Now let us today go ahead with the next concept, that is, let us understood the effect of moment of resistance in this particular equation. So if you want to go ahead, let us understood what is the moment of resistance. The neutral axis of any transverse section of a beam is defined as the line of intersection of the neutral layer with the transverse section. It is also written by neutral axis. So when a beam is subjected to the pure sagging bending moment, stresses will be compressive at any point above the neutral axis and tensile stresses below the neutral axis, and there is no stress at neutral layer or neutral axis, that we have discussed also in the previous case. Hence, the stress at a distance y from the neutral axis is given by F is equal to E over R into y. So, the figure shows the cross section of a beam. This figure shows, and let neutral axis be at the neutral axis of the section. Consider a small layer at a distance y from the neutral axis. Let dA is the area of layer. This layer, the area is dA. So, force on this layer is equal to stress multiplied by the area, because we know that the stress is nothing but the force divided by cross sectional area. So, force is equal to stress multiplied by area. So, our intention is to find out the moment. So, before finding out the moment, we have to find out the force on the layer. So, force on the layer is nothing but the stress which is acting on a layer multiplied by the area of layer. What is the stress acting on the layer? That is the F. What is the area? That is, or the layer, that is dA. So, F, we know the equation, that is E over R into Y and dA. So, this is an equation of force which is acting at a particular layer at a distance y from the neutral axis. Now, these forces will have moment about the neutral axis. The total moment of these forces about the neutral axis for a section is known as moment of resistance. Let us, I will discuss this term once again. The total moment of these forces, because this is an equation of a force, then our intention is to find out what is the moment acting at that particular layer. Then our intention is to find out the total moment for a full section of these forces is known as moment of resistance of a particular section. So, moment of the force about neutral axis is equal to force on layer multiplied by y. Now, let us discuss the fundamentals. What is the meaning of moment? Moment is defined as force multiplied by perpendicular distance from the application of force. So, it is nothing but the force on the layer multiplied by perpendicular distance. What is perpendicular distance from neutral axis? Is y. So, we know the force on the layer, that is E over R into y into dA multiplied by y. Now, y into y, that is y square. So, we achieve moment of the force about neutral axis is E over R into y square into dA. Now, total moment of the forces on the section of the beam is by integrating this simple equation, because this equation E by R into y square into dA is applicable to a particular layer. By combining all the layer, I have to do the integration. So, total moment of the forces on the section of the beam is equal to integration of E over I y square into dA, while the term E over R, that is E divided by R, that is the modulus of elasticity divided by the radius of curvature, is constant for a particular cross section. So, E by R, which is remaining outside of the integration, and E by R integration of y square dA. Now, this total moment is defined as M. So, M is the external moment applied on the beam section for the equilibrium of the moment of resistance offered by the section should be equal to the external bending moment, and that is M is equal to E over R integration y square dA. This y square dA represents the moment of inertia of the area of section about the neutral axis. So, this integration y square dA is nothing but I, that is the moment of inertia. So, if we replace this term integration y square into dA by I, then our equation is m is equal to E by R into I. Therefore, if we rearrange the terms, we got an equation m over I is equal to E over R. But we already know from the previous equation that E over R is equal to F over Y. So combining these two terms, we get m over I is equal to F over Y is equal to E over R. I will repeat once again this term. M over I is equal to F over Y is equal to E over R. This equation is known as equation of bending equation. It is a fundamental equation, that is m over I is equal to F over Y is equal to E over R. Now let us once again we simplify the equation. We know that m is equal to F over Y into I. Then if we take together the term, is m is equal to F into I by Y, where I by Y, that is the ratio of moment of inertia to the distance from neutral axis. Repeat, I by Y is I moment of inertia to the distance from neutral axis is known as section modulus. It is termed as Z. So Z is equal to I by Y. So finally an equation we got in terms of the moment of resistance is equal to m is equal to F into Z. So finally we achieve m is equal to F into Z, where Z is equal to I divided by Y. So let us go ahead and we prove that neutral axis coincides with centroidal axis. So we achieve an equation that is a purely bending equation. That equation is m over I is equal to F over Y is equal to E over R. Before we proceed, let us be understood each and every term